So in this video, I want to take a few moments to talk about the calculus of exponential functions. So my big purpose in this video is just to try to review what it means to take the derivative or the integral of some exponential function. Now I want to take a moment to really focus on the really important one for the moment, which is the natural exponential function, which is base e. So the function's e to the x. Now this is a very special function, as you'll see, because both its derivative and its integral are all the same thing. It doesn't matter what process I apply to this, what calculus process, if I have e to the x, it always remains the same. So that's always a really cool fact about this particular function. So now that I've mentioned that, I want to just kind of prove to you again very quickly that this is in fact true. So what I'm going to do is I'm going to prove this by trying to take the derivative f prime of x using the difference quotient, which is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So in this case, we're going to do e to the x plus h minus e to the x divided by h, and I'm going to remember to put my limit out front. Let me do that. All right. Limit as h approaches 0. Now, important thing to remember here is whenever you are adding inside of an exponent, this is the same thing as multiplying the two bases together. So I'm going to rewrite this. The limit as h approaches 0 of e to the x times e to the h minus e to the x, all divided by h. So all I did was I split up this added exponent into two separate multiplication of the bases, e to the x times e to the h. All right, next step I'm going to do is I'm going to factor out that e to the x from the numerator, so e to the x times e to the h minus 1 divided by h. Since this e to the x at the beginning has nothing to do with the limit as h approaches 0, I can take that all the way out of the limit. And at this moment, I'm at e to the h minus 1 divided by h. Now, there's not a really good, I'm going to use the word algebraic way to finish solving this problem. So I'm going to give this to you guys of just saying, hey, we could graph e to the x minus 1 divided by x and see what the limit as x goes to 0 is. Or we could try plugging in some numbers. We could make a table and test some numbers that are smaller than 0, test some numbers that are bigger than 0, and see what happens. Well, I'm going to tell you right now, if you find this limit here, you're always going to get the number 1. So it's essentially e to the x times 1, which gives me a final answer of e to the x. So my argument here is that if I take the original function and I find its derivative, it is the same function. Now, again, the reverse process, the anti-differentiation, the integral, should take me from the derivative back to the original function, so e to the x goes right back to e to the x. I'm going to recap this in a second, so just wanted to point that out. Now, I want to transfer this basic information of the natural exponential function, the really important one, to generalizing it to any exponential function, no matter what the base is. Now, if it's an exponential function, we do need a couple of things. Number one, the base has to be a positive number. It has to be greater than 0. Can't be 0, can't be negative. It also can't be 1 because essentially 1 to the power of x just gives you 1 all over again. It doesn't really follow a rule for exponential functions. Now that I've got that defined, we're going to try to take the derivative of this function, and I'm going to do it using the chain rule. So I'm going to rewrite g of x as e to the ln of b times x. And the reason I'm going to do that is essentially the e to the exponent of a natural logarithm, those two things cancel each other out. We've got the natural base exponent, we've got the natural base logarithm. Those two things are inverse operations, so essentially it would just leave me back down as b is my base and x is the exponent. Now that I've got that handled, if I go to try to take its derivative, we're going to end up doing the chain rule with what this exponent is, but from this last example, the natural exponential function that I did here in blue, we know that if I try to take the derivative of this big function, this e to the exponent, I should get the exact same answer back where I started. So I'm going to have e to the ln of b times x. And again, I needed to apply the chain rule to this exponent, which is taking the derivative of ln ln of b times x. Since this is actually a linear function, ln of b is just a number, times x to the first. When I take the derivative of that, it just turns into the number ln of b, whatever that may be. So we're going to have e to the ln of b times x times the natural log ln of b. Again, I'm going to switch this back out. E to the ln should bring me back down to base b to the exponent x times the natural logarithm of b. Now, that means that if I have any base, whether it's, let's just make up a number, let's call it 2 to the x. If I have 2 to the x, my derivative down here would still be 2 to the x. I just need to now multiply it by the natural log of 2. Okay, so the question is, how do I undo this process? Well, think about it this way. Is if when I take the derivative, I multiply by the natural log of b. If I want to go backwards, if I want to integrate this, I should divide by the natural log of b. So let me kind of recap all of that important information down here. So if I take the derivative of the exponential function e to the x, I get e to the x. If I do the integral of e to the x dx, I get e to the x plus, since this was an indefinite integral, we're going to include our constant of integration. And if I take the derivative of b to the x, I get b to the x times the natural log of b. If I integrate b to the x dx, I get b to the x divided by the natural log of b plus our constant of integration. Now, be aware, some of these problems may involve things like the chain rule for derivatives, or the constant multiple rule, or any other kinds of rules for derivatives, or even, if I'm talking about integrals, we might have to do something like U substitution, or one of our other methods for calculating integrals. But this is just giving you the basic setup of these functions. Hopefully this helps